Welcome back to our study of networks and distributed systems based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. We're in Module 5 at this point, which is a discussion of the link layer. We just finished studying about how a host is able to send packets to other hosts on a subnet and across subnets. Now we're going to do some exploration of Ethernet, the dominant link layer technology in use today. Ethernet is the dominant LAN technology today. In the 1980s and in the early 1990s, Ethernet was just one of several popular local area technologies, including token ring, FDDI, fiber distributed, and asynchronous transfer mode, or ATM. But since its invention in the mid-1970s, Ethernet has continued to change and improve and hold on to its dominant position in these LAN technologies. There are a lot of reasons for Ethernet's success. First, Ethernet was the first widely deployed high-speed local area network. Because it was developed early, network administrators became very familiar with Ethernet and were reluctant to switch over to other LAN technologies when they came on the scene. Second, token ring, FDDI, and ATM were much more complex and expensive than Ethernet, which further discouraged network administrators from switching over. Third, the most compelling reason to switch to another LAN technology, such as FDDI or ATM, was usually the higher data rate of the new technology. However, Ethernet has always been able to produce versions that operated at equal data rates or higher. Switched Ethernet was also introduced in the 1990s, which further increased its effective data rates. Finally, because Ethernet has been so popular, Ethernet hardware has become cheap. The original Ethernet local area network was invented in the mid-1970s by Bob Metcalf and David Boggs. It used a coaxial bus to interconnect the nodes as we see in this figure 5.20.1. Bus topologies for Ethernet persisted until the mid-1990s. Ethernet with a bus topology is a broadcast LAN. All transmitted frames travel to and are processed by all adapters connected to the bus. In that bus technology, all hosts are competing to send frames on the bus, which of course can result in collisions. You remember that we covered Ethernet's carrier sensing multiple access collision detection protocol with binary exponential backoff earlier. By the late 1990s, most companies and universities had replaced their LANs with Ethernet installations using a hub-based star topology. In such an installation, the hosts and routers are directly connected to a hub with twisted pair copper wire. A hub is a physical layer device that acts on individual bits rather than frames. When a bit representing a 0 or 1 arrives at one interface, the hub simply recreates the bits, boosts its energy strength, and transmits the bit onto all other interfaces. This means that a hub is simply a multi-port amplifier. Therefore, Ethernet with hub-based star topology is also a broadcast LAN. Whenever a hub receives a bit from one of its interfaces, it sends a copy out on all of its other interfaces. If a hub receives frames from two different interfaces at the same time, collisions occur and the nodes that created the frames must retransmit. In the early 2000s, Ethernet installations continued to use a star topology, but the hub at the center was replaced with that linked layer switch that we've talked about. We'll be examining switched Ethernet in depth later in this module. For now, we only mentioned that a switch is not only collisionless, but is also a bona fide store and forward packet switch. Unlike routers, which operate up through layer 3, a switch only operates through layer 2. The Ethernet frame is shown in figure 5.20.3. Let's consider sending an IP datagram from one host to another host with both hosts on the same Ethernet LAN. Let the sending adapter, adapter A, have a MAC address of AA-AA-AA-AA-AA-AA, and the receiving adapter, adapter B, have the MAC address BB-BB-BB-BB-BB. The sending adapter encapsulates the IP datagram with an Ethernet frame and passes that frame to the physical layer. The receiving adapter receives the frame from the physical layer, extracts the IP datagram, and passes the IP datagram on up to the network layer. Let's examine this frame. The preamble field is 8 bytes. The Ethernet frame begins with an 8-byte preamble field. Each of the first 7 bytes of the preamble has a value of 10101010, and the last byte is 10101011. The first 7 bytes of the preamble serve to wake up the receiving adapters and to synchronize their clocks to that of the sender's clock. Why should the clocks be out of synchronization? Keep in mind that adapter A aims to transmit a frame at either 10 megabits per second, 100 megabits per second, or 1 gigabit per second, depending on the type of Ethernet LAN. However, because nothing is absolutely perfect, adapter A will not transmit the frame at exactly the target rate. There will always be some drift from the target rate, a drift which is not known by the other adapters on the LAN. A receiving adapter can lock into adapter A's clock simply by locking into the bits in the first 7 bytes of the preamble. The last 2 bits of the 8th byte of the preamble, the first 2 consecutive ones that we heard, alert adapter B that more important information is about to come. The destination address field is 6 bytes long. This field contains the MAC address of the destination adapter, BB-BB-BB-BB-BB-BB. When adapter B receives an Ethernet frame whose destination address is either that series of BBs or the MAC broadcast address, it passes the contents of the frame's data field to the network layer. If it receives a frame with any other MAC address, it discards it. The source address is 6 bytes. This field contains the MAC address of the adapter that transmits the frame onto the LAN, which is in this example was AA-AA-AA-AA-AA-AA-AA. The type field is 2 bytes. The type field permits Ethernet to multiplex network layer protocols. To understand this, we need to keep in mind that hosts can use other network layer protocols besides IP. In fact, a given host may support many network layer protocols using different protocols for different applications. For this reason, when the Ethernet frame arrives at adapter B needs to know to which network layer protocol it should pass, that is, demultiplex, the contents of the data field. IP and other network layer protocols each have their own standardized type number. Furthermore, the ARP protocol has its own type number, and if the arriving frame contains an ARP, the ARP packet will be demultiplexed up to the ARP protocol. Note that the type field is analogous to the protocol field in the network layer datagram and the port number fields in the transport layer datagram. All of these fields serve to glue a protocol at one layer to a protocol at the layer above. Now the data field can be anywhere from 46 to 1500 bytes. This field carries the IP datagram. The maximum transmission unit of Ethernet is 1500 bytes. This means that if the IP datagram exceeds 1500 bytes, then the host must fragment that datagram. The minimum size of a data field is 46 bytes. This means that if the IP datagram is less than 46 bytes, the data field has to be stuffed to make it fill out the 46 bytes. When stuffing is used, the data passed to the network layer contains the stuffing as well as the IP datagram. The network layer uses the length field in the IP datagram header to remove the stuffing. The cyclic redundancy check, CRC, is 4 bytes. As we talked about earlier, the purpose of the CRC field is to allow the receiving adapter, adapter B, to detect bit errors in the frame. All the Ethernet technologies provide connectionless service to the network layer. That is, when an adapter A wants to send a datagram to adapter B, adapter A encapsulates the datagram in an Ethernet frame and sends the frame into the LAN without first handshaking with adapter B. This Layer 2 connectionless service is analogous to IP's Layer 3 datagram service and UDP's Layer 4 connectionless service. Ethernet technologies provide an unreliable service to the network. Specifically, when adapter B receives a frame from adapter A, it runs the frame through a CRC check, but it doesn't send an acknowledgement when the frame passes the CRC check, or send a negative acknowledgement when a frame fails the CRC check. When a frame fails the CRC check, adapter B simply throws it out. As a result, adapter A has no idea whether its transmitted frame reached adapter B and passed the CRC check. This lack of reliable transport at the link layer helps to make Ethernet simple and cheap. But it also means that the stream of datagrams passed to the network layer can have gaps. If there are gaps due to discarded Ethernet frame, does the application at host B see the gaps? As we learned in the module on the transport layer, this depends on whether the application is using UDP or TCP. If the application is using UDP, then the application host B sees all the gaps in the data. On the other hand, if the application is using TCP, then TCP in host B will not acknowledge the data contained in the discarded frames, causing TCP in host A to retransmit. This is a good time to take a break. So let's take a few minutes, review your notes, update your study guide, and when you're ready, come on back and we will move to the next video.